Alright. Hi guys, today we're gonna talk about attentions in transformers. Transformers don't generate a single fixed output. Instead, they predict the probability distribution over all possible next words. One key factor in this process is the temperature parameter. This controls how certain or random the predictions are. A low temperature makes the model more deterministic, meaning it always chooses the most probable words. This results in stable but sometimes repetitive outputs. In other words, in other way, a high temperature introduces more randomness, allowing the model to generate creative and diverse outputs, though sometimes at the cost of coherence. For example, in a chatbot, a lower temperature setting might give precise and factual answers, while a high temperature setting could make the conversation feel more natural and varied. Understanding how temperature affects prediction is crucial when fine-tuning transformer-based models. Next slide is byte pair encoding, which is called BPE, and tokenization strategies. Before a transformer can process text, it must first break it down into tokens, which is smaller and manageable units. One widely used method for this is byte pair encoding, which is BPE. Instead of splitting words arbitrarily, BPE merges the most frequent character pairs into a single token. This has several advantages. First, it prevents the vocabulary from becoming too large, reducing memory usage. Second, it helps the model handle real words effectively by breaking them into known subword units. For example, instead of treating unhappiness as a unique token, BPE might split it into unhappy and ness. This allows the model to generalize its knowledge of related words like happiness and unhappy more efficiently. Words, in their raw form, are just sequences of letters, but for a transformer to understand them, they must be converted into high-dimensional vectors, as known as word embeddings. What makes transformers unique is their ability to adjust these embeddings dynamically based on context. This means that the same word can have different meanings depending on the sentence it appears in. For example, consider the word bat in these two sentences. I saw a bat flying in the sky. I swung the bat to hit the ball. A traditional model might treat bat the same way in both sentences, but a transformer refines the embedding based on surrounding words, ensuring that the correct meaning is captured. This context awareness is a key reason why transformers outperform older models in tasks like translation and text generation. Transformers rely on the attention mechanism to determine how strongly each word in a sentence relates to the others. This is done using two key mathematical operations. First is dot product. Each word in a sentence has a query vector which it compares to the key factors of other words using a dot product. A higher result means stronger relevance. Second one is softmax function. The computed similarities are converted into probabilities, ensuring that the model focuses more on important words while minimizing attention to less relevant ones. For example, in the sentence, the fluffy blue creature roamed the forest, the word creature should focus on fluffy and blue to understand its characteristics. The attention mechanism ensures this happens by assigning the higher probabilities to these words. Single-head attention captures only one type of relationship between words, which can be limiting. To solve this, transformers use multi-head attention, which is a technique where multiple attention mechanisms run in parallel, each learning different aspects of the sentence. For example, one head might focus on grammatical structure, like subject-verb agreement. Another might track semantic relationships, such as synonyms or related concepts. A third might identify long-range dependencies, like references to earlier parts of the text. By combining these different perspectives, multi-head attention allows the transformer to capture richer, more meaningful representations of language. After attention has been applied, the next step in a transformer is the feed-forward neural network, which is FFN. Each token in the input sequence is passed through an FFN, which consists of two linear transformations where the model applies learned weights, and a non-linear activation function like ReLU to introduce complexity. The purpose of the FFN is to further refine the representation of each token, ensuring that the model can capture deeper patterns and relationships in the data. Training a transformer involves multiple key steps, each crucial for improving the model's performance. First, preparation. The model is trained on vast text datasets like books, articles, and web pages. Second part is tokenization and embedding. The input is broken into tokens and converted into vectors. Third part is forward pass. The model predicts the next word based on previous words. Next part is loss calculation. The predicted word is compared to the correct answer and an error is measured. Last part is backpropagation and optimization. The model adjusts its weights using Adam Optimizer, allowing it to improve over time. This cycle repeats millions of times, enabling the transformer to develop a deep understanding of human language. One of the reasons transformers outperform traditional models is their ability to scale efficiently. Unlike RNNs, which process text sequentially, transformers process entire sequences at once thanks to their self-attention mechanism. This allows them to, first, leverage parallel computing. Transformers make full advantage of GPUs and TPUs for faster training. Second, it can handle massive datasets. The architecture is designed to scale with increasing amounts of data. Lastly, it enables real-time AI applications. Many modern AI models like GPT-4 rely on this efficiency to generate text instantly. As AI continues to advance, these scalability improvements will be essential for building even more powerful models. To wrap up, let's summarize the key takeaways from today's discussion. First, transformers have revolutionized NLP by replacing sequential models with parallel processing. This enables faster and more efficient language models. Second, the attention mechanism allows the model to focus on relevant words, improving performance in tasks like machine translation and question answering. Finally, scalability and efficiency make transformers ideal for large-scale AI applications, powering models like GPT-4 and BERT. Looking ahead, research is focused on reducing computational costs through optimized architectures and enhancing contextual reasoning to improve AI's understanding of language. Finally, addressing ethical concerns to ensure fairness and reduce bias in AI systems. In short, transformers have reshaped the AI landscape, and their evolution will continue to thrive in the years to come. All right, this is all for today. Thank you.